We are in section 5.2, binomial probability distribution. Experiments in which only two outcomes are possible are referred to as binomial experiments, provided certain criteria is met. An experiment is said to be binomial if 1. The experiment is performed a fixed number of times. Each repetition of the experiment is called a trial. 2. The trials are independent. This means that the outcome of one trial will not affect the outcome of the other trials. 3. For each trial, there are two disjoint or mutually exclusive outcomes. We call them success or failure. And 4. The probability of success is the same for each trial of the experiment. Let the random variable x be a number of successes. N is the number of trials in the binomial experiment, and x is called a binomial random variable. So notation that we use when dealing with the binomial probability distribution, there's going to be n, independent trials of the experiment. P is going to be the probability of success for each trial, and then that means that 1 minus p, which is also called q, is the probability of failure for each trial. X is denoting the number of successes in n independent trials of the experiment. So x is somewhere between 0 and n, and it could equal either one of those. The example that we have next says determine which of the following probability experiments represents a binomial experiment. If the probability experiment is not binomial, state why. So part A says the experimental drug is administered to 100 randomly selected individuals with the number of individuals responding favorably recorded. And so if you notice, we have a set number of trials. So we have 100 randomly selected individuals. That's our trials. People are independent of one another. And so that's another thing that we need to check. We also need to see if there's two outcomes, and those outcomes need to be mutually exclusive. So it says either favorably is how they are responding to this, or other would be unfavorably. And we would assume that since these are people, that they would have the same probability of dealing with this drug. So this is an example of a binomial random variable. And so part B says a random sample of 15 college seniors is obtained, and the individuals are asked to state their ages. So this is an example of one that is not binomial. And the reason why this is not binomial, easiest thing to look at, is that we are asking about ages, and there's more than just two ages. So we don't just have two outcomes. We have quite a few outcomes. So there's more than two outcomes for part B. C says 500 randomly selected U.S. parents with at least one child under the age of 18 are surveyed and asked if they have ever spanked their child. The number of parents who have spanked their child is recorded. So again, we have this time 500 parents that we surveyed. Parents, again, people are independent of one another. They are asked if they've ever spanked their child. So there's two disjoint or mutually exclusive outcomes, spanked or not spanked. And the probability of spanking or not spanking for each person would be the same. So this is an example, again, of a binomial experiment. The next example that we have says when an adult is randomly selected with replacement, there is a 0.85 probability that this person knows what Twitter is based upon results from a Pew Research Center survey. Suppose that we wanted to find the probability that exactly 3 of the 5 randomly selected adults know what Twitter is. So part A says, does this procedure result in a binomial distribution? So there's 4 things we have to check. So the first one is going to be that we have a fixed number of trials, and there are 5 trials. There's 5 different people that we're going to survey. So we have 5 trials. Since we are dealing with people, the trials are independent. The third thing is asking yourself, is there 2 mutually exclusive or disjoint responses that these people are going to give? And yes, they either know or don't know. There isn't a kind of no option. The next thing is that the probability of success is fixed. And this time we do have a number. It says there is an 85% or a 0.85 probability that they're going to know what Twitter is. So probability is equal to 0.85, and this is fixed. It's the same for everybody. So therefore, we can say that it is a binomial distribution. Part B says, if this procedure does result in a binomial distribution, identify what the values of n, x, p, and q are. So since it is, we are going to identify n, x, p, and q. So n is the number of trials, which is 5. X is the number of successes, and we wanted exactly 3 of those. P, we actually have written up above. P is 0.85. And then Q would be the probability of failure, so opposite of success. So we're going to go ahead and use that complement rule and do 1 minus 0.85, and we get 0.15. So this is what we're going to have to identify before we start any other example that has us continuing on with this process. So when sampling without replacement and the sample size is no more than 5% of the population, treat the selections as being independent even though they are actually dependent. So definitely something we need to know. So we have a binomial probability distribution. And this is our function that we have. And so the probability distribution function is obtained when we have x successes and n independent trials of a binomial experiment is given by, and if you notice we have combination of n choose x, p to the x, 1 minus p to the n minus x. X is going to be a value between 0 and n, and p is the probability of success. Next thing that we have, there's a table here. And this is just to kind of help you guys out to look at on your own. With all of us having different mathematical backgrounds, and all these words being used quite often throughout now and the rest of the semester, it's a good idea to kind of look these over and make sure you have an understanding of what these words mean and what mathematical symbol goes with them. The next example I am going to circle, and we will work on this one together in class. And then we get into how to use a calculator in order to do a lot of this work. So we're going to go ahead and give this a star. This is obtaining a binomial probability using an 83 or an 84 calculator. And we have two things. The first one's going to be the probability that x is equal to x. And the second one is going to be the probability that x is less than or equal to x. So if you notice for both of these, you're going to go to second vars. And you'll notice you're going to either use binomial PDF or binomial CDF, depending on which symbol it is that we have. If you notice, the one that we don't have, and we're going to add it in over here on the right, is what happens when we have a greater than. And so we would have the probability that x is greater than our x value that we have. We are going to be using the complement rule, so this is going to be 1 minus the probability that x is less than or equal to x. And so those are going to be the 3 different things that we have. 2 of them found by the calculator, and that third one is one that we're going to have to kind of rewrite and think about a little bit different. So the next example that we have says, according to flightstats.com, American airline flights from Dallas to Chicago are on time 80% of the time. Suppose that there are 15 flights that are randomly selected, and the number of on-time flights is recorded. So part A says, find and interpret the probability that exactly 10 flights are on time. So we're reading these words. It does say find and interpret the probability that exactly 10 flights are on time. So what does the word exactly mean? So exactly means it would be equal to. And so when we have x is exactly equal to 10, so using our calculator steps that are listed up above, I know I'm going to be using binom PDF. I also need to know not only x is equal to 10, but I also need to know n and p in order to do this. So n is the total number of flights that we have that we are surveying, and we're surveying 15 total trials. And then we also have p, which is that probability of success. And for us, the probability of success is 80%. So let's go ahead and write that as a decimal, so 0.80. And for part A, our x value, it literally says it in here how we wrote it. X is equal to 10. So take a second and put all this in on your calculator. So we're going to go to second vars and go down to binom PDF for part A. Our trials that we had, our value for n is 15. Probability was 0.80. And our x value that we have for this is 10. Select paste. If you have an older style calculator, this is how you would type that in. Selecting enter. And again, since this is a probability, we will round this 4 decimal places. So we get 0.1032. Part B says find and interpret the probability that fewer than 10 flights are on time. So this time we have fewer than 10 flights, and we are still dealing with the probability. So the word fewer means less than 10. So since part A was equals to, we used binom PDF. And since part B is less than, we're going to use that binom CDF for a cumulative distribution function, so adding up it and everything before it. So fewer than 10. And so we have, this is going to be equal to, and if you notice really quick, the sign is very similar, but we have less than 10, and it needs to be written as less than or equal to. And since this is discrete data and we're counting the number of flights, to rewrite this as probability of x is less than or equal to, the value that it would be less than or equal to would be 9 flights. And so again, using binom CDF, we still have the same n value and the p value, which is listed up above. That did not change. But our x value this time is 9, and again, using binom CDF. So we're going to go second vars. And for part B, this is going to be using binom CDF. So binom CDF. Our trials are 15 still. Probability is 0.80. And for this one, our x value is equal to 9. Paste. And again, this is what it would look like if you had an older style calculator. Select enter. And we're going to go ahead and round that to 4 decimal places, so 0.0611. Rounding our probability 4 decimal places, we get 0.0611. For interpreting both of these, an interpretation for the first one is that there is the probability that exactly 10 flights out of 15 flights are on time is 0.1032. And interpreting part B would be the probability that fewer than 10 flights that are on time is going to be out of 15 is equal to 0.0611. So you can take a second to write those on your own. The next one says find and interpret the probability that at least 10 flights are on time. So probability that at least 10 means 10 or more. So we have x is greater than or equal to 10. And since we are dealing with a greater than or equal to, we are going to have to be using what we wrote up here on the top that we added in. And so I need to look at this as a 1 minus and use that complement idea. So 1 minus, so since I'm looking at 10 or larger, that means 10, 11, 12, 13, 14, or 15, I could take all those probabilities since they all sum up to 1 and subtract away the stuff I don't want, which would be 9 or less. And this is actually what we calculated up above. So I'm just going to go ahead and steal that number there and plug that in, and we're going to get 0.9389. So interpreting this would be that the probability that at least 10 flights out of 15 are on time is going to be 0.9389, so about 93, almost 94%. Part D says find and interpret the probability that between 8 and 10 flights are on time. So the probability that between 8 and 10 flights are on time. And there's different ways to do this. So what we can do is find the probability of x equals 8 plus x equals 9 plus x equals 10 and add those all up. Another way to do this is to take probability that x is less than or equal to 10 and subtract away the stuff that we don't want. So right now we say 10 or less, but I don't want anything less than 8 or less than or equal to 7. So I'll say less than or equal to 7. So we have to do binom CDF twice. Second, vars. And we need binom CDF. And trials is 15. Our probability is 0.8. And our x value is going to be 10. I'm going to paste that. You can select enter here, but I'm just going to go ahead and do subtract, so minus. And I'm going to go ahead and put the second one in. So second, vars. Going again down to binom CDF. 15.8. That stays the same, but our x value on the next one is 7. Selecting paste, hit enter one more time. And rounding this 4 decimal places, we get 0.15999. So that's going to make that be 0.1600. We get 0.1600. Interpreting this would be that the probability between 8 and 10 flights are on time out of 15 flights is equal to 0.16. The next thing that we have on here is going to be the mean, which is also called the expected value that we saw earlier, the variance, standard deviation for the binomial distribution. And so we have a binomial experiment with n independent trials and probability of success p has a mean equal to n times p, a variance equal to n times p times 1 minus p, and a standard deviation equal to the square root of that variance formula that we had up above. It is very important to interpret and understand the mean and the standard deviation so that the range rule of thumb and the rare events rule for inferential statistics can be helpful. And so the range rule of thumb, and this is again what we've been seeing for the past few chapters, is going to be a significantly low value is if it's less than or equal to mu minus 2 sigma, significantly high value is greater than or equal to mu plus 2 sigma, and values that are not significant are between those two values that we would have. And so the next example on here says between 1974 and 2011, there are 460 NFL football games decided in overtime, and 252 of them were won by the team that won the overtime coin toss. Assuming that winning the overtime coin toss does not provide an advantage, then the probability of success of winning would be 0.5, and the probability of failure or losing would also be equal to 0.5. So part A says find the mean and the standard deviation for the number of wins in groups of the 460. So the formulas that we had were right up above on the previous page. And we have the mean is equal to n times p, and the standard deviation is equal to the square root of n times p times 1 minus p. Another way to think about this is also n times p and 1 minus p can also be written as q. So find the mean and find the standard deviation. So our mean is equal to n times p. N is the 460 games that we have times 0.5 is going to be equal to 230 games. Our standard deviation from the previous page is going to be the square root of n times p times 1 minus p. I'm also going to write it as n times p times q. Same thing, q is the same thing as 1 minus p. So we have 460 times 0.5 times 0.5. And working this out, we get 10.72 games. The next part here says use the range rule of thumb to find the value separating the number of wins that are significantly low and significantly high. And so we're going to have, to separate our significantly low values is going to be mu minus 2 sigma. Significantly high values are going to be mu plus 2 sigma. And so we have mu minus 2 sigma and mu plus 2 sigma. And substituting in what we had up above, we had a mean of 230 minus 2 times 10.72. And then 230 plus 2 times 10.72. Working both of these out for our cutoff for our significantly low, we get 208.6 games. And significantly high cutoff would be 251.4 games. And so it says use the range rule of thumb to find the value separating the number of wins that are significantly low and significantly high. So significantly low would be anything lower than 208.6 games. Significantly high would be anything larger than 251.4 games. So the next part down here, part C, says is the result of 252 overtime wins and 460 significantly high. So yes, because it's greater than, so because it's greater than that cutoff that we had, so greater than 251.4 games. So we still have another way to look at this. We can use probabilities to determine when results are significantly high or low. So there's always two ways to kind of look at significantly high and significantly low. So significantly high numbers of successes is when X successes among N trials is significantly high if the probability of X or more is less than or equal to 0.05, and significantly low is going to be if the probability of X or fewer is less than or equal to 0.05. So that probability of it happening is really small, and that cutoff that we have is 0.05 for both of those. So the next example that we have is data on M&M weights, and this is an example that we will work out together in class.